Let me show you how to be a good Bayesian.
Today, I'm honored to welcome Haavard, Roux, and Janet van Niekerk, two researchers at the cutting edge of Bayesian computational statistics. Haavard, a professor at KAUST, is the person behind Integrated Nested Laplace Approximations, or INLA, a robust method for efficient Bayesian inference that has transformed how we approach large-scale latent Gaussian models. Janet, a research scientist at KAUST, specializes in applying INLA methods to complex problems, particularly in medical statistics and survival analysis. In this conversation, Haavard and Janet guide us through the intuitive and technical foundations of INLA, contrasting it with traditional MCMC methods and highlighting its strengths in handling massive, complex datasets. We dive into real-world applications ranging from spatial statistics and air quality control to personalized medicine. We also explore the computational advantages of stochastic partial differential equations, discuss penalized complexity priors, and outline exciting future directions like GPU acceleration and advanced sparse solvers. This is Learning Bayesian Statistics, episode 136, recorded May 13, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com. Haavard, Roux, and Janet van Niekerk, welcome to Learning Bayesian Statistics.
Thank you.
Thank you.
Yes, and thank you for tolerating my pronunciation of your name. Well, I'm getting there. I love this podcast also because it's very cosmopolitan, so I get to kind of speak a lot of different languages. I'm super happy to have you on the show today because I've been meaning to do an episode dedicated to INLA per se for a few months now. I've mentioned it here and there with some guests, but now today is the INLA episode. So let's do this. But before that, maybe can you let's start with you, Janet. Can you tell us what you're doing nowadays and how you ended up working on this?
Okay, good. Thank you for having me. What I'm doing nowadays, so I work in the INLA group at KAUST, and we do a lot of things that pertain to INLA, and we also do some other Bayesian things. How I got to work at the INLA group, I just sent an email to Haavard when I finished my PhD, and I said, well, I don't know what to do next. Can I come and visit you? And he said yes, and I came, and then I started to work here, and that's how I ended up here.
That's a long time ago.
Yes, more than 7 years ago, yeah.
Okay, damn.
Yeah.
And Haavard, what about you? What are you doing nowadays, and how did you end up doing that?
Nowadays, I try to keep up with the rest of the people in the group. So how I ended up here at KAUST, you mean?
No, mainly how you ended up working on these topics, because I think your name is pretty much associated with INLA, so
Yes,
I'm
yes.
curious how this all started. What's your origin story, basically?
Okay, yeah. It started like 25 years ago. So we're doing a lot of this market chain Monte Carlo. And we're trying to do, essentially working on this, what we now have as a latent Gaussian model. We're trying to really solve this market chain Monte Carlo issue to get good samplers. Working a lot with this Gauss-Markov random fields to get these sparse matrix computations, all these things. And then we kind of come to an end and you're realizing this is not going to work. In the sense that this MCMC, even if we can do like a big, we can update everything in one block, everything is efficient as it could, but it's still way too slow. And then we wrote a book about this thing. And then you see in the end of that book from 2005, there is a short outline of how to proceed. And it's basically kind of computing the results from the proposal distribution that we had at that time. And that's how things got started. And then PhD student Sarah Martino, she joined. That was January 2005. And from that point, I've been working on this, Yeah, it's over 20 years ago. From INLA started and another 5 years before that where we did all the prep work. Yes. In parallel to that, you also have Finn Lindgren who's joined. He's working on the spatial models, but yeah, that's also all connected. Yeah.
Yeah, quite the big adventure. And actually, Haavard, could you? Well, no. Let's go with Janet, and then I'll ask Haavard about a follow up with that. But Janet, for listeners who are unfamiliar with INLA, so first, that stands for Integrated Nested Laplace Approximations, if I'm not mistaken. Could you give us an intuitive explanation of what that is and how it differs from traditional MCMC methods?
Yeah, sure. So in MCMC methods, what you essentially need to do is you need to keep drawing samples, and at some point, these samples will come from the distribution you're actually looking to find. And then from those samples, you can calculate things like the mean or the mode and so on. So INLA, what INLA does is it actually approximates with mathematical functions the posterior in its totality. So there is no sampling, waiting for things to arrive at the stationary distribution. You compute the approximation and then you have the posterior. So then you can from that get also the mean and the credible intervals and so on. So it's a deterministic method. It's not a sampling based method, which is why it's fast. But yeah, essentially that's kind of how it works.
Yeah, thanks. That definitely cleared that up. And I'm curious, actually, Haavard, when you started developing INLA, I think from your previous answer, basically you were motivated by making inference faster.
Yes.
But
yes,
also
yeah.
what, like, was that the main challenge you were trying to address, or was that also, like, were there also other challenges you were trying to address with INLA?
No, it was simply trying to, yeah, as I said, first we tried to make MCMC work because at that time, early 2000, believed that this was the way to go, and then you're realizing it's not. At some point, you make a switch. It's like MCMC is not going to work. It's never going to give us the kind of the speed that we need. And then we started on these approximations and working our way through that one. And that has been the goal all the time, to make this inference for these kind of models fast. Yeah, fast is more important than, yeah, to make them quick. These have been to make them quick, kind of scalable in a way. And there are two types of scales. In a way, you can scale with a number of data points. We can also scale with a number of the model size itself. So these are two different things. And in the first version of INLA, we kind of scaled okay with both of them. And now in the second generation of INLA, then we scale way better, both with respect to model size and also the data size. So that's another redevelopment. But yeah, that's
Nice, yeah.
it's a second generation in that. So it was almost like a complete rewrite. And we bumped the main methods. Yes.
Yeah, this is super exciting. I mean, we'll dive a bit more into that during the rest of the show. But yeah, high level, I think now we have a good idea of what that's helpful for. I mean, what's that doing? But I want us to also dig into the cases where that could be helpful. So, Janet, actually, I'm curious. How did you personally get introduced to INLA, and what drew you to this particular computational approach before we dive a bit more into the use cases?
Yeah, so I did my PhD in Bayesian statistics, and the main focus was kind of to write samplers for covariance and correlation matrices. So of course that doesn't go well. No matter which sampler you write. So I think very similar motivation, just there has to be kind of a better way to do this, even if you lose a little bit of generality. For specific cases, you have to be able to do better. And that's kind of where I started looking into approximate methods like ABC for the likelihoods, and there is VB and so on, and then INLA specifically, which combines many different approaches together, just to do things the same kind of accurate, but just faster.
Okay, yeah, I see. And actually, I read while preparing the questions for the show that latent Gaussian models are particularly suited to INLA. So I'm curious why, and also more in general, which cases are particularly appropriate and you would recommend to the listeners to give a try, to give INLA a try. So maybe Janet, you can take that one, and Haavard, if you have anything to complete afterwards.
Sure. So actually, a latent Gaussian model, this is the assumption on which INLA is built. So INLA is developed to do inference for latent Gaussian models. So if you do not have a latent Gaussian model, then none of the math will hold, because it's developed to do inference for latent Gaussian models. Okay.
So can you maybe just briefly explain to listeners what a latent Gaussian model is?
Yes, I have to say, when I started at KAUST with Haavard, we had another colleague, Håkon, which was also Norwegian, and he did his PhD with Haavard. So it was me and them two. And at the first few months, it felt like they spoke a different language. Even though I had a PhD in statistics, I could not figure out what's latent Gaussian model and all these things. So I totally get this question when it comes up. So what is a latent Gaussian model? Okay, a latent Gaussian model is when you have data points for which you can assign a likelihood, and maybe the mean or some parameter in the likelihood will have a regression model. Okay, this regression model can contain fixed effects, random effects, different components. And conditional on the model, the data is then independent, so that the likelihood is then just this product. So
Right.
where the
So it's
latent
like
Gaussian
this-
part, sorry.
Yeah, no, exactly. I was gonna
Yeah. So it's
give you
like
the
a
segue
GAM.
to go there.
It's like a GAM up to now, right? Like if you have a GAM. Then the latent Gaussian part comes into the fact that all the fixed effects and the random effects should have a joint Gaussian prior. So if you can think of any random effect like an IID random effect or like a time series model. As long as they have a Gaussian joint distribution, then they will be a latent Gaussian model. So it, at first thought, it might seem like, oh, this is like a very restrictive class, but it's actually not. A lot of models that we use every day are actually latent Gaussian models. And even some very complicated models, like survival analysis models, they're also latent Gaussian models, a lot of them. If you do like co-regionalization, where you have spatial measurements at different locations, you can model them jointly, and this is also a latent Gaussian model. So it's really much broader than you would think initially.
Yes.
Yeah. Thanks, Jan. It's super clear. That makes me think about, state space models where most of the time you need linear Gaussian state space models. So that means latent Gaussian likelihood and Gaussian innovations. So like basically what you just talked about here, even though the structures of the models are different. And yeah, as you were saying, that may seem pretty restrictive, but that actually covers a lot of the cases. I guess some cases that can be more complicated are when you have count data.
No, they are the same, actually.
Okay.
So the likelihood has no
you
restriction.
Could have a binomial. Okay.
Yeah,
okay,
it can
so
be any likelihood. It can be a zero inflated likelihood. You can have multiple likelihoods.
Nice.
Like you can do a multivariate data analysis. Each data type with their own likelihood, as long as the latent part, so just the fixed effects and the random effect, should have a Gaussian prior. But what you put on the data, that there is no restriction on that.
Nice. Okay, so it's less restrictive than the classic Kalman filter then, because the classic Kalman filter only can take normal likelihood. So okay, yeah, that's really cool. And then I agree that's even more that's even less restrictive than what I had understood. Haavard, it looked like you had something to add.
No, it's Janet explained everything. It's of course, if you have one latent Gaussian model, if you have another one, you can put them together. So you also can do these kind of joint models where you share kind of effects. So all these kind of joint models is also covered. As soon as you have one, you can also do two, and then you can combine them together. So it's almost like, I think it's easier to classify all the models who are not latent Gaussian model. Is that it's a very surprising result in the sense of when you write it down, it looks so simple, but actually to make the connection from the model that you have to rewrite it in that form we need it's many struggle with that, because the form is so simple. You have some parameters like variances, correlations, over dispersions, and then you have something Gaussian, and then you have observations of the Gaussian, and that's it. So this structure covers almost everything that is done in practice today. You can say, okay, mixture models, this kind of thing is not in the class. Yeah, but they are not that much used, in the sense of in daily life of people who are working with this. Like more in research, yeah, you can do it. It's a little different, but in the practical life of people who do these things, it's not. So it's a very, very surprising thing.
Yeah. No, for sure. I mean, as soon as you start being able to handle normally distributed likelihood and count data, you have, I would say, 80-90% of the use cases. Like mixtures are indeed, they are possible, but they are way less common for sure.
Yeah.
And actually, Harvard, you've been doing that for quite some time now, as you were saying. So I'm curious what you've seen as the most impactful applications of INLA, especially maybe at extreme data scales, because that's really where INLA shines.
Janet, help me out. You know this better.
Yeah, so I mean, we've had the World Health Organization has used INLA for some air quality control methods. We've had the CDC used INLA for like epidemiology. We've had the Malaria Atlas project use INLA to model the prevalence of malaria and to kind of help inform interventions and where they should be. And for instance, I mean, we are past COVID, but a lot of people still work on COVID. And I just checked quickly this morning, and there is more than 800 papers who used INLA for COVID modeling. So yeah, I mean, there's a lot of impactful applications, but on a very large scale, there has been applications. Recently, there is a paper by Finn Lindgren and others who've used it to model temperature on the global scale with lots and lots and lots of stations, and they can do a very high resolution model. So like Howard said before, the kind of modern framework for INLA that came like after 2021, it can scale now very, very high with data.
Nice, yeah. And actually, I'm wondering, like, when you say people are using INLA to model these data sets, what do they use? What's a package you recommend people check out if they want to start using INLA in their own analysis?
So the INLA methodology is implemented in the R INLA package. So it's an R package. There is a Python wrapper, or soon there will be, or it is there, but anyway. So there will soon be like a Python wrapper where you can use INLA in Python. So
nice.
yeah, I think, yeah, most people just use the R INLA package, and Haavard does a great job. There's kind of almost a new testing version every few days. So the development is very, very fast. Usually the package is faster than the papers. Like we would implement something, and then a year later the paper would come out explaining what was changed. So users always have the latest version immediately.
Yeah, this is super cool. So the R INLA package is in the show notes already, folks, for those who want to check it out. So yeah, check out the website. There are some examples in there, of course, of how to use it and so on. And if you guys can add the Python wrapper to the show notes, that'd be great, because I think, yeah, definitely that will increase even more your number of users. I know I will use that because I mainly code in Python. So yeah, like that's for sure something I will check out. Haavard, anything you want to add on that?
No, I think it's fine. It is what Jan say. But we are not on this C-run. We are not on this public repository or the standard R repository, simply because the R code is just a wrapper. So inside there is a C code. It's a program that runs independently, and this is simply too complicated to compile on this automatically built system. So we build it manually and include it in the package. And for this, because it's contained a binary, then it cannot be in this kind of public repositories. So we have our own that you need to kind of download from.
Okay, yeah, damn, that adds to maintaining complexity. So thank you so much for
Yes.
doing that for us. I know it can be complicated. And Janet, actually, I think if I understood correctly, you apply a lot of a lot in medical statistics and survival analysis. So can you share with us maybe an example of how you've done that and why INLA was particularly efficient in this setting?
Yes. So when I started at KAUST, actually Haavard told me we need someone to do survival analysis with INLA. So that's kind of how it started. And I think up until that stage in 2018, there was very few, maybe 2 or 3 works on using INLA for survival analysis. But actually, the survival analysis models are also latent Gaussian models. But to make this connection is not so clear at first glance. Like, you really have to just sit down and think about your model on a higher level to be able to see the connection to a latent Gaussian model. And of course, if we can then use INLA, then we can do a lot more complicated models. Like, we can do spatial survival models, which a lot of survival packages cannot do. We can do then these joint models. We now have another package built on top of INLA called INLA Joint that has a very nice user interface for joint models. So where you have something that you monitor over time, so an event, it could be like a relapse of cancer, for instance, and then you would have many biomarkers, like lots of blood test values and maybe X-ray image and so on. And you would have a lot of these longitudinal series, and then you would jointly model them and assuming that there is some common process driving all of this. And these models are very computationally expensive because, you know, you have a lot of data, a lot of high velocity data. You can have multiple biomarkers. You have this hazard function that you model, which is different than general linear models where you model the mean, because we don't model the mean time to an event. We model the hazard function, like this instantaneous risk at every time point. But then if you can see that your survival model or your very complicated joint model, even if it contains splines over time or it contains a spatial effect, different IID effects like multi-level random effects for hospital effect and doctor and patient and so on, you can easily see that this model becomes very complicated if you want to just do the right thing. But then INLA makes it possible that we can actually fit these models. And one thing that we've been trying to do in this regard in terms of medical statistics is to really position INLA to be a tool in kind of the drive to personalized medicine. Because in the end, if you want a doctor to run something locally and see, okay, the probability for relapse is lowest on medicine A versus B and C and D, you need something that's gonna run fast, like it cannot come out tomorrow. So that was kind of a main motivation to kind of position INLA towards medical statistics also, to just show the potential to actually achieve this personalized medicine target.
Yeah, this is really cool. Yeah, definitely agree that has a lot of potential, basically, because that makes more complex models still like practically inferable, whereas with classic MCMC it wouldn't be possible. So yeah, that expands the universe of Bayesian models in a way. So that's really fantastic. Actually, in something I'm wondering, Haavard, is the computational challenges. Are there any such challenges when you're using INLA? Numerical stability, efficiency of the algorithms, all these diagnostics that we get with MCMC samplers, how does that work with INLA when you're running a model? How do you know that conversions was good? How do you diagnose the conversions? How do you handle convergence issues? Are there even convergence issues? How do you go about that practically?
Yeah, the convergence issue is very different. This is like a numerical optimization. So if it doesn't work, you will be told that this doesn't work. Over the years, this has been code been developed for 20 years, so we are getting a good experience, what is working, what is not. Of course, there is a specialized version and tailored version of everything, even numerical optimization algorithm. We don't use just a library. The code is from some kind of other standard library, but is tailored to exactly what we want. Just computing gradients, we do it in a very different way. That is also tailored to what we do. Everything is kind of tailored, every kind of custom made, everything kind of refined, so that it's amazing how well it runs, in the sense that if you have any decent model will run. If it has problem with convergence, it's usually because you have a model that, to be honest, doesn't make sense. Sense in the way that you have very little data. You're using vague priors. There is no information in the model. There is no information in the data, and then this is harder. So about convergence is like this is kind of different from kind of markov chain Monte Carlo, where you have to do kind of diagnostics. In here is more if you if you do the optimization, this is on the highest level. On the parameters on the top, we're talking variance, correlation, over dispersion, this kind of parameters. If you go to a point that is a well-defined maximum, then essentially you're good. And we're looking around that point to correct for kind of skewness that is not perfect, kind of symmetric in that sense. And these are also kind of small diagnostics, but they are never. It's never a kind of serious issue that it was for MCMC. No. So now it's like if you put something reasonable in, you get something reasonable out. There's very little. I don't think we have serious convergence issues. No, I don't think so. We might had it like 15 years ago or 10. In the beginning, there was more trouble computing gradient Hessian, this kind of thing. But now we do this very differently. We are being smarter. And then no, there isn't any. It works pretty good actually. Yes. So everything is is different. Yes.
Cool. Yeah. I mean, that's great to hear. And Janet, maybe do you have any tips to share with the listeners about that?
No, I think I will just comment on like the gradient. There is a paper describing the gradient method that's used in INLA. It's called smart gradient, describing how this kind of gradient descent methods and so on work with this different type of way to get a gradient. And it is really good. It's also the one we use inside INLA, but of course, people who use gradient-based methods would also benefit from that as a standalone contribution.
Yeah. Okay. Yeah. Thanks, Janet. That's helpful. And feel free to add that to the show notes if you think that's something that's going to be interesting for our listeners. And Haavard, actually, I read that you've applied stochastic partial differential equations. So it's called them SPDs. Very poetic name. And so, yeah, you've used that mainly for spatial modeling. So can you give us an overview of why these SPDs are interesting? And I think you use that to model Gaussian fields. So yeah, maybe if you can
Yeah,
talk a bit more
yeah,
about that, because that sounds super interesting.
yes. So normally Gaussian fields are like normal distributions described for the covariance or a covariance function. This is a traditional way of doing things. And there is nothing wrong with that, except that it's not very smart way of doing things, often the case. And like in the beginning, like 20, 25 years ago, there was this was also one of the problems we wanted to solve. In a way, some of these kind of spatial stat problems. But of course, there is a version, there are models that are kind of Markov. Markov in the sense that instead of the covariance matrix, you're working with the precision matrix, the inverse of the covariance, and that is sparse. So this was often called these regional models or Markov models. And then you had the kind of the spatial models, the Gaussian field with kind of return covariance. You choose a covariance function, and they were dense, and they were kind of a mess. And then, of course, it's like in parallel to the development of INLA, this now professor in Edinburgh, Finn Lindgren, who's also part of this overall INLA project. He started, or him and me started to work on this thing because we had like, I think we had the first version in 1999, a proof of concept that most of these models for spatial model was almost Markov. They were almost Markov, but we had to fit them kind of numerically. And from that point, we can kind of move on to working with precision matrices instead. And this is one of the key things in INLA, that you don't work with covariance, you work with precision, because precisions can be put together. This is like it's like playing with Lego. You have one component, you have another one, you just stick it together, and it's easy. If you work with covariance, there is a lot of math computations that go in just to put them together. So this falls directly out. Additional to this, you have the fact that they are Markov. You mentioned the state space models, where if you condition on pass, you only need the latest one. This really simplified computations, and of course, these apply more generally. And these are called Gauss-Markov random fields. And yeah, this connect back to the book we had 20 years ago, 2005, with Leonard Held. And the point is that the computations are very efficient for these kind of models. So instead of using dense matrices, you can use algorithms for sparse matrices. And these scales way, way better. So back to the SPD thing, then there was a there was a hunt for trying to solve this in more again, the motivation was computational speed. We need to do things faster. And Finn, he's a small genius. And no, he figured out that, okay, we can connect these to this stochastic differential equation. And this go actually back to very old work in the late 50s and early 60s that show that these Gaussian fields are exactly solutions of these stochastic differential equations. As soon as you realize that, then you can say, okay, let's solve this thing. We don't need to solve them. We need to represent the solution of it. And that is done by this finite element method from applied math. And then you get something that is sparse. And the matrices you get there will be our kind of precision matrices. So everything up to that point was done for computational speed. And we can do things faster. Of course, when at some point you're realizing the most important thing about this SPD approach is not the speed, is actually that you can use this way of thinking to do things very easily that was up to that point almost impossible. And now it's just, of course we can do it. It's like having, Janet mentioned this postdoc Håkon Bakke that was here in the beginning. He worked on these barrier models. What happens if you have islands and you want the dependence to go around the islands or through following rivers, and do this adjust for the coastline and all this thing. This is super complicated. Unless you do it with the SPDs, then it's just follow from the definition. It's very little things you need to do, and then it's just do the right thing. And also this is connected to the kind of the physical laws that we think these kind of processes were almost, or they will follow or almost follow. So it's like stochastic differential equations. So it's just more or less elliptic ones that we make kind of stochastic. No, so this is super useful. But of course, the complexity is way higher. It's way higher. You need tools to create the mesh. You have to work with a mesh. You have to work with triangulation of an area. You have to do all these kind of things. But Finn has written all these kind of tools for doing that. He's also pretty good in this coding, you know. And as soon as you have the tools, everything of this is quite easy. But there is a huge kind of step to take before you get to that point. But when this is done, when somebody has done it for you, then it's pretty easy. Yeah. Also, these have been very useful. Also, you can do these non-separable models going in time as well. You just have a time dependence of this, and this follow the same procedure.
Yeah. Damn. Yeah, for sure. That sounds like a big project, but really fascinating. If you have any link you can share with us in the show notes, that'd be great, because I think that make for a very interesting case study that we can follow along.
It's a very large project. It's like if you're giving kind of tutorials courses on this thing, you can almost have half of the time is spent on the INLA package itself, and the second half is on this SPD thing. Well, of course, this is integrated, but the kind of the complexity of that part is of the same order as the complexity of the whole INLA package itself. You know?
Right. Yeah. Janet, to get back to you, I'm curious, like given your experience in applying Bayesian models, especially in complex medical scenarios, what new features or improvement, if any, would you most like to see incorporated into INLA?
So I'm probably biased, but I think the new implementation or the new methodology, the new INLA methodology, has solved a lot of issues that was there before. Because a lot of the medical statistics models are very data heavy and not model size heavy. For instance, if you think about MRI data, you have many data points, but maybe not so many parameters. And in the classical INLA from the 2009 paper, this did not scale so well to very many data points. But now the new implementation scales extremely well. And I think for instance, in medical problems, especially medical imaging, INLA, the new INLA now can be applied to that, whereas before it could not. So in my biased opinion, there is not anything I see at the moment that I would like to be incorporated. There are still many applications that can be explored and see how far we could push this kind of new INLA, I would say.
Mm-hmm, mm-hmm. And Harvard, kind of a related question. What do you see since you're developing the package at the forefront? What do you see as the next major frontier for INLA, whether that's methodological advancement or new application domains?
Yeah, I think that the most pressing issue now is to have a better sparse solver that is more scalable, is scaled better in parallel, and is also able to kind of start taking advantage like everything with GPUs, you know. Now GPUs are everywhere and it's coming, they are really good and we need to take advantage of them. But this is not easy. It's not easy at all. So there is a one postdoc in the group, Asmal Tata. He's been working on a new implementation of a new sparse solver that is targeted towards this. So it's more a modern design, has modern ideas, and this is going really well. So to have this kind of a better numerical kind of backend supporting this kind of calculations, this has been a main struggle for a long time. The thing is that sparse matrix solvers are not as, can I say, developed. It's easier to work with if you're doing supercomputing, then working with dense matrices is far more easier and it's far more kind of relevant. This very large sparse matrices is less relevant. So therefore, there are fewer implementations. Those who are often kind of, some of them are close, not open source, and they don't scale too well in terms of in parallel. You know? Because nowadays, it's like with all the modern machines we have now, it's a lot of problems is more about memory, not about CPU. It's more important to have the data you want to multiply. You have them right there in front of you, and then you can do it instead of doing fewer computations, you know. So it's like memory management and this kind of everything with memory is much more important now than it was before. So then looking at the sparse matrix as instead of a sparse matrix of just elements, you can look at that as sparse matrix of dense blocks. And this dense blocks is called a tile. So then you can work with these small dense blocks instead. Even computing too much, but it's faster to do that than figuring out only what needs to be computed. And that's the key thing. And this scales way, way better. It can connect to GPUs and connect to all these things. Yes. So there are, in fact, in the group, there are works in two directions of this. One is to kind of build a new sparse matrix solver to be directly into the INLA code that is now. We also have initiative on writing a completely distributed solver. This is another postdoc, Lisa. She's doing that with some colleagues in Zurich to have a complete distributed solver written essentially in Python. You know? That also have this ability, you could distribute the calculations, you have GPUs, this can take care of this, and yeah, this is aimed for a different data scale. So we have to work on two parallel tracks. One is to kind of keep the current code developing, and the other one is try to prepare also for the future, or maybe also for larger models. They need different things. So I think that's main pressing issues. As Janet said, there is a lot of things that was a problem before. The problem is things that we would like to have slightly better, but now I think they are basically solved. So there are the two main things are developing applications, as Janet said, but also this more modern computing to get this integrated. It's also the major task. But this is to write a new solver take years. It's years of work. It's not something you do in a weekend. It's a scale of years.
Yes. That sounds about right. But definitely looking forward to seeing these advancement in the coming month and years. Janet, since you've been there, at some point you've been a beginner of INLA, you had to start somewhere. So I'm curious, for listeners who want to get started with INLA, what resources or practices would you recommend as first steps?
I think this also depends a little bit on why you want to learn it. So if you want to use it, you're going to be like an applier of INLA. On the website, there are links to some tutorials that people have done, but also the papers we do from the group always have code available. On the website, there are a few open source books. There is one book from Virgilio that goes through a lot of common models with code. So it's written like R code, the output, and so on. The book is in this format. So if you want to learn how to code INLA and where to get the posteriors from and so on, then that kind of book is a very good tool. Then to learn really what is INLA, not just to be able to use it. I think this is a little bit harder. I think we've tried, since we have developed the new methodology, we've tried to write it up in a way that's easy to understand. But there is also this gentle introduction. This is the one I used. It's also linked on the website. It's called A Gentle Introduction to INLA. But yes, this will be on the old methodology. But it just gives a good intuition, how it's different and questions about convergence and so on, and kind of makes it clear that it's not based on samples. So everything with samples, that comes with samples, is not there. But then what is there if there is not samples, and how it works and so on. And something that's really nice, that I think maybe a lot don't know initially, is that you can always draw samples after, because you have the full posterior. So if you need to calculate whatever for some reason, you can draw samples. So you can still have samples. It's not like, oh, they're now, we have a built-in way to draw samples from an INLA object. So it's very versatile in that way, that you can have the samples, but it's not based on samples. It's based on math, I would say.
Yeah. That all makes sense. Thanks, Janet. Haavard, anything you would add here to basically recommend resources to beginners?
It is, as Janet said, there are a few books out there that they're also open. You can read them just on the web. They are pretty good. We have one. This is more targeted towards these SPD models. It's all book about only these. There is introductory. Yeah, there are several of these books to the background theory. This is, as Janet said, this is less clear because there is a development. And there is a series of key papers. You have to read one, and then you do another one, and do another one, and do a third one, and then you do another one that we do a lot of things, and there's another one. It's like a sequence of things. So less, that is, I understand this is less clear, and the first thing you do is to read the book about Gauss-Markov random fields, So that's a harder thing. I see that because it contains a lot, There is a lot of things going on. For us, I don't think we see it anymore because, but you're realizing because we have been working on this a lot. But I understand there is a lot of concept, there is a lot of things that you just put together, if you put on top of each other, is new things. It's a lot of details, and many of the details are never written down, because where should you write them? No journals would have them. So it's like there are these things. It's like it gives a kind of skeleton, and then you have to figure out everything in between yourself. But it's basically there. But it's hard. I see it's kind of hard to get a complete picture of what is going on. Maybe we have to write another book in the end, with all the details.
That sounds good. Yeah. And maybe another question I had that's very practical, but is there any difference in the way you set appropriate priors when you're using the INLA algorithm for inference compared to when you would use Stan or PIMC to run your models? Or is that pretty much the same? It's just the inference engine under the hood is changing.
Yeah, so you can set your priors whatever you want, but of course the latent ones has to be Gaussian, but you can set like the parameters of the Gaussian if you want. But then also we have default priors. So you can run your model without putting any prior inside, and a lot of Bayesians I've spoken to says this is really bad because then I don't know what's going on. But for practitioners, a lot of them just kind of want to run a model and not make a decision really about priors. So this brought up a whole new field of research, I would say, within the INLA group, because if we need to decide on a default prior, we have to make sure that this works. And the definition of works is what, So generally, I think in the field I see this a lot, maybe not so much in the Bayesian statistics community, but more in the applied community, where people would choose a prior. That's kind of the most used prior in the literature. And they just use the other papers as motivation. I choose this prior because everybody else has chosen it, right? And this has caused that we've ended up with a lot of priors that's been used for like variances and so on. That's really bad, but has been accepted because everybody else have used them. And a lot of the priors we use for hyperparameters or nuisance parameters, I would say, like variance components and so on, their initial motivation often was to be a conjugate prior. But then if we are anyway doing something like MCMC, where we code and we have a computer, then the idea of conjugacy is a little strange in that sense, right? So kind of the motivation for this gamma, let's say gamma prior, for this inverse variance. The motivation was different when it was proposed, but it's still used because it's been cited in 5,000 papers, right? So this opened up the idea of, okay, but what should we then do? What should we put as a default prior that works well? And this is how the idea of penalizing complexity priors, or in short it's called PC priors, were born. So how can we derive and propose priors for all these hyperparameters that are not in the latent part of the model, that we know will do a good job in the sense that they will not overfit. So for instance, if you include a random effect in your model, let's say just an IID effect, you use the variance or the estimated variance to see how big is the random effect, right? But if you have a prior that's never going to be able to estimate a variance that's small, then you could get a larger variance just even if it's not true. But if your prior does not have sufficient mass to take it small, then you're going to get a big value for the variance, thinking this random effect is important even when it's not. So the PC priors are developed for each type of these parameters. It's not like uniform prior on all of it. Like you have to derive it case by case. But essentially what they do is they will shrink the parameter to the value where it means the model is going to be simpler. So, and this value depends on what the parameter is. So for instance, for the Weibull model, if you have one of the parameters equal to 1, then it's actually the exponential model. But then if you think about it, you will almost never estimate it equal to 1 for any data. Even if you simulate from exponential data, you will not estimate it to be 1. So the penalizing complexity prior will put a lot of mass then, for instance, at 1. But it's derived based on the distance between the models. So we put a prior on the distance between the models, not directly on the parameter, because the distance we can understand. So the default priors in INLA for the hyperparameters, most of them are PC priors. So even if you don't set the prior and use the default, now the defaults are mostly good. There's still some development at the moment going on, especially for priors of correlation matrices. But in general, most of them have good default priors now.
Okay, this is really cool. Yeah, I didn't know you were using PC priors for that by default, but yeah, like can definitely vouch for them. Also, like not only because they have these great mathematical properties that you're talking about, but also they are much easier to set because they have a more intuitive explanation. So I know they are derived differently for different parameters, but I use them all the time now when I'm, as you were saying, setting standard deviations on varying effects. So basically the shrinkage factor of the random effects. And yeah, so that's an exponential, and then there is a formula that at least I hard coded in Python that's coming from the paper. I guess that's what you did in INLA. And also I use that for the amplitude of Gaussian processes, which are basically the standard deviation of Gaussian processes. So yeah, that's the same. And I really love that because you can think about them on the data scale. So it'd be like, I think there is a 60% chance that the amplitude of the GP is higher than X. X being a number that you can interpret on the data scale. And that makes it much, much, much easier to think about for me. So yeah, this is awesome that you guys do that. Actually, do you have any readings we can link to in the show notes? Because the only thing I know about are like some papers who talk about penalized complexity priors, but they are not super digestible for people. So yeah, I don't know if you know about code demonstrations that are a bit clearer, and also which penalized complexity priors are appropriate for different kind of parameters.
Yeah, we have some works like for specific things, so I can link them in the show notes for sure.
Yeah, for sure. Because I mean, that's not only still quite new research, but yeah, it still hasn't distilled yet a lot in practice. But I think it should be faster because these are extremely helpful and practical for people. So yeah, that's awesome that you guys do that. I really like that, and I think it's also something we want to try doing on the PIMC side to be able to make it easier for people to just use PC priors. Awesome. Damn. Haavard, anything to add on these priors or in general,
No,
or PC priors in particular?
no, but it is exactly what Janet say. It's like at some point you're realizing you need some kind of structured framework to think about priors and to derive priors. And this is not guessing a prior. This is like you're putting up like principles, how to think about them, and then you can derive them. It's just become math. And you know they work in the same way all the time, because it is the same thing. It's about distance between distributions, and whether this is parameterized by a parameter in standard deviation or log precision, it's the same prior, because in distance scale it's the same. It's just materialized differently for different parameters. But the scary part is that, at least I realized that I don't understand parameters. If I see a parameter and see a prior, how does this effectively impact the distributions? I can try, but I'm not very good at it. So I don't trust myself. I trust this distance-based thing because it's doing the same thing all the time. And this was also derived, how many years? 15 years? No, 10 years ago? More than 10 years ago. Yes. That was in Trondheim. A key person there was also Daniel Simpson. That was part of this group. Yeah, so great guy. Yeah.
Yeah.
No, so
Yeah.
this really solves this, because before that point, I think our kind of stand was, okay, prior is not my problem. If you want this prior, it's your problem, you know. But at some point, it's actually become your problem, because you're realizing how a lot problems come from bad priors. And then you cannot think about this this kind of standard priors that is kind of asymptotically best. They often define it that way. So you have to do the math and you have to let something go to infinity, right? To make sense of this thing. And then you want prior that doesn't do anything. You know, you have all these things that's usually the standard, but we want the prior to do something. We just want to prevent it from doing bad things. You know? So these priors are derived not to be the best. They are these priors you can use when you don't know what else to do, and they are never bad. So if you're doing kind of how do they perform against other things, they're always on the top three, you know. They are never bad. You know? They just do the same thing because they are derived from this distance way of thinking. So no matter how you do the parameterization, whether you look for over parameterization, over what's dispersion and negative binomial, you're looking for variance, it's all the same thing. You don't need to understand the things, you can just understand the concepts of distance. And as you said, Andrea, you can connect it to a property of the data. That you have to do some kind of calibration, you have to set some kind of scale. And this is what you do. The rest, the math is doing for us. No, it's really nice things. But there are still parameters that had bad default priors because there is no general good one, and we don't want to change whatever was there. But usually, most parameters have some kind of a PC prior you can use. Yes, which make life easier. Yes.
Yeah, I mean, I completely second everything you just said here, Haavard, and I think it's also very telling that somebody very mathematically inclined and experienced as you are still has difficulties thinking about how the different parameters interact in complex models. And
Yes.
and that means everybody has that problem. I definitely have it, and it's like, yeah, sure, I can always put a prior on that standard deviation or that covariance matrix, but once you start being deep enough into the layers of a model, you don't really know how that impacts the model. And the only way you can do that is mainly through painstakingly going through prior predictive checks. So that's still possible, but that's a bit inefficient. Sometimes there is no other way, but I'm sure there are a lot faster and better ways most of the time. And PC priors give you the Pareto effect on that. So yeah, folks, let's try and start using that, all of us, instead of going blindly choosing our priors. I think it's a good way to start closing up the show, actually. Before I ask you the last two questions, is there anything you wanted to talk about or mention that I didn't get to ask you?
No, I would just say that honestly, I think if you have a latent Gaussian model, there's nothing better you can do to infer your model. Honestly, you cannot. Basically, you achieve the accuracy of MCMC, but really in almost real time. So, really, if you have a latent Gaussian model, just try it. And if you need any help, there is a R INLA discussion group. I also linked it in the show notes. And Haavard's very good at replying almost instantly. And there are also others that reply. So if you try INLA and there's anything that comes up that you're unsure, just send them email to that group.
Yeah.
Nice. Yeah. Great. Fantastic. Thank you so much, folks, for taking the time. That's really wonderful. Before you get to go to bed, because it's very late for you, so again, thank you so much for that. I will ask you the last two questions I ask every guest at the end of the show. So first one is, if you had unlimited time and resources, which problem would you try to solve? So, Haavard, do you wanna start?
I think I would try to solve the problems I'm working on now. It's like we are in a situation here where we have quite good resources and we are able to do this kind of trying to solve this kind of problem that we have. So I think I would just stick to those, I'm good. Yes.
Yeah, that's great. I mean, I'm sure people can hear you're passionate about what you're doing, so I'm not that surprised. Janet.
Yeah, I think, we have a lot of interesting problems already, and KAUST makes it very easy to work on big problems. We have a very nice academic environment, so I don't know if there is any big problem I can think of to solve.
Awesome. Damn, that's cool, folks. And well, Janet, since you have the floor, let's continue with you. If you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Okay, this is quite hard because I have had dinner with a lot. So, thinking about someone I've not had dinner with and who's also South African, I would love to have a dinner with either Trevor Hasty, who's still alive and he is a South African, or Donnie Krieger, who was the inventor of kriging, and he was also a South African. So one of these two would work for me.
That sounds good. And Haavard, what about you?
Yeah, if I could choose, it would be nice to meet Isaac Newton. But he's been away for a long time. I think he must have been quite special. So I'm not sure if it would be a very pleasant experience, but still, it would be nice to to meet someone like him, you know, just meet him. Yeah, I don't think it would be an experience, you know.
Yeah.
Yes,
Yeah.
I think so. Yes.
Yeah, for sure. That sounds very interesting. And yeah, at least you could talk English to him, so that's maybe there would be some vocabulary difficulties, but at least you would have
I
English
think
in
so.
common. Yeah.
Yes.
Amazing. Damn. Well, I think we can call it a show. I'm super happy because I had a lot of questions for you, but we could cover everything. So thank you so much, folks, for that. Thank you so much also to Hans Moncho for putting me in contact with you guys. He was like, "Oh, you should talk to this group. They are doing amazing work." So thank you so much, Hans, for the recommendation and also for listening to the show. You obviously have good taste. And well, on that note, thanks again, Janet and Haavard, for taking the time and being on this show. And as usual, we'll put a lot of links, folks, in the show notes. So if you were interested and want to dig deeper, make sure to check those out. Janet, Haavard, thank you again for being on this show.
Thank you.
Thank you. It's been very nice. Thank you.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.